Hi guys, Dr. Burns here. We're going to look at section 4.3 today, which is getting more into linear trends, and we're going to talk a little bit more about the model that we're using when we talk about these scatter plots, and that's called the regression line. So make sure your cell phone is put away and turned off and you're ready to listen and take notes. So first of all, we're talking about the relationship between two numerical variables. And remember, we're focused on linear relationships and linear trends in this section. So the model we would use for that is called a regression line. So it's a tool for making predictions about the relationship between two numerical variables. What happens, or what do we think will happen as the x variable increase? What do we think will happen to the y variable? It has the form y equals b plus mx. And I know this is the way you're not used to seeing the equation of a line. You probably usually write it as mx plus b, but it's the same thing. Our textbook writes it this way in this order, so I'm going to go with that. It's, like I said, StatCrunch does the same thing, so I'm going to stick to that order. B is the y-intercept and m is the slope, just like it would have been in algebra. And we're going to use StatCrunch to get the equation for the regression line. One thing that's a little unique to statistics versus your algebra classes, we're not going to actually use y and x, at least in this textbook. We actually use the names of the variables. So let me give you an example here. The scatter plot below shows the average number of years in school compared to hourly wages taken from census data in 1970. So we have two numerical variables, the number of years in school versus hourly wages. Can you imagine? $3.50 an hour, back in 1970. So we've got two numerical variables, and this is our linear relationship. You can see the linear trend in the data, and that line that's graphed there is your regression line. Describe the trend for this data. So I would say it's definitely a positive trend. And then it says, suppose that R equals 0.883. Would you consider that to be a strong or a weak trend? That's pretty close to 1. And again, that's a little subjective. I would say anything for our purposes above like 0.7 or 0.75, I would consider that to be fairly strong. So what does this tell us about the relationship? That it's a strong relationship. So we could say something like, as the number of years in school increased, the hourly wage tended to increase as well. I'm using past tense because we're talking about 1970. Tended to increase as well. There may be exceptions, but generally that's what appeared to happen. Changing the order for x and y variables will change the regression equation. So that is important, and that should make sense. If I change x and y, that's going to change my slope, that's going to change my y-intercept. The r stays the same, but the equation itself will change. And there's several terms we use when we talk about the x and the y variable. I know you've heard some of these. X we may also call the independent variable, whereas if x is the independent, y would be the dependent. We may also call x the explanatory variable, and then y would be the response variable to that. Another term we might use is predictor for the x, and the one that we predict, so the predicted, becomes the y variable. And you'll hear me use those interchangeably, so make sure you're familiar with those terms. Now, how do we interpret the equation? So the slope, let's start with that. How do we interpret the slope of the equation? This is very, very important, and I want you to remember this because we're going to use this a lot. And if you do go on to say business calculus for your major, this idea of interpreting slope becomes very, very important. So let's really make sure we understand this. We can think of the slope of the regression line as telling us how much the y variable changes when the X variable is increased by 1 unit. And that's very, very important, that relationship. So how much the Y changes when we increase the X by 1 unit, 1 additional unit. A regression line with a slope close to 0 means that there is no linear relationship between the X and the Y variable. Similar to when we said R was close to 0, same idea for the slope. So it says, an example, at some previous example, we did the association between a car's mileage and its sales price was modeled with a regression line. I think this was one we did in class the other day. The regression equation was given by this function. So here's what this would look like. This is your Y. Price in this case is Y, and miles is your X, your independent variable. And this is how StatCrunch will give us the equation of the line. Sometimes they'll put parentheses around this. You'll see it written that way. Sometimes they'll put a little dot in between them. But make sure you're clear that miles is your independent variable and price is your dependent variable. So the slope is always the number in front of the independent variable. That's really important that you recognize that. Just like back here, mx. X is the independent variable. So m is the coefficient for that variable. And it's in words, in this case, as miles. So first of all, identify it. The slope is negative 0.034. I personally really like to, when I write the slope, write it as over 1. To me, that really hones back in on this definition. Think about the numerator is the change in Y, just like it was in algebra class, whereas the denominator would be the change in X. Whatever this number is, we can always put it over 1. That never changes the value of it. So how would we interpret this? We would say for every additional unit for the X value, right? So for every additional 1 unit, so for every additional 1 mile in this case, because that's the X variable, on the car, the price drops or tends to drop by, and why am I saying drops? Because this is negative. That means we have a negative correlation. So as the mileage goes up, the price of the car tends to go down. How much does it go down by? That's what this numerator tells you. So the price drops by 0.03, about 3 cents, basically. And I'm going to say on average, because we want to be a little open-ended there. So for every additional 1 unit increase in the mileage, the price will go down by about 3 cents is what we're saying. Let's talk finally about the y-intercept. So remember, the y-intercept is the other variable, or the other number rather, in the equation. So that's the number that's by itself. So the y-intercept is the value when x is 0. Just like it was in algebra. I really want you to make the connection to what you did in your algebra class. If we have a graph, x and y, remember the y-intercept is where we cross the y-axis and the corresponding x value is 0. So the y-intercept is always the value when x equals 0. The y-intercept is only meaningful if it makes sense for x to equal 0. In other words, in the context of the question, does it make sense for x to be 0? It totally depends on the question and what the variables are. Continuing with let's go with this previous example. So continuing from the last example, interpret what the y-intercept means. Well, in the last example, first of all, the y-intercept, what number is it? It's that 15,867. That would be the price of the car when x equals 0. So when the miles equals 0. Does that make sense? Can a car have 0 miles on it? Well, yes, right? When would a car have 0 miles on it? When it's brand new. That's what that means. So this would be when the car was brand new. Now, as we go through, sometimes this will not make sense. If we're talking about heights, for example, somebody's not going to have a height of 0. That doesn't make sense. If we're talking about sizes for different things. Someone's not going to have a size of 0 if you're talking about a measurement of some kind. And we'll see some examples where it makes sense and some where it doesn't make sense. So we'll do a little bit of practice with this in class. I'll see you tomorrow.